Alright, hello everyone. So today we're going to discuss some applications of lenses um, and, and then some lens related questions. Alright, so a simple application is the camera. Now you guys are familiar with the digital camera that everybody has. Mostly in every cell phone nowadays we can see a camera in it. There's much more complicated DSLR cameras, the bigger ones, the old-fashioned film cameras. I don't know whether you have seen those. Either way, the main principle behind a camera is having a convex lens focusing incoming light into a film or some kind of sensor behind the lens. So as you can see in this PowerPoint diagram, there's some basic parts. There's a lens, there's a shutter, there's a film or electronic sensor. So for an example, let's say you're taking a picture of a tree, right? So this is the object, and the object is emitting light. In this case, a tree is actually reflecting sunlight, so light comes in and it's reflecting, right? There's light coming in. So here we have the lens. The light that comes in bends and creating an upside down image, so probably something like this. Now this image in the camera, now this lens is inside the camera. There is a screen on the back. In the old-fashioned cameras, it was a film, has some chemicals on it, so the incoming light kind of prints an image on it. It burns the chemical into a shape, and then later you can develop it. In the modern ones, there's a digital series of like sometimes millions of them, digital sensors behind the screen. So they capture incoming light, the brightness, the color, and then you can recreate the image. So here you can see a simple everyday application of lenses. In this case, it's a convex lens. You have to create real images in order to capture them into a film. Okay, so let's see what next slide says. In digital cameras, they use CCD sensors. So this film over here, it contains an array of pixels like this, and CCD stands for charge coupled devices. So it's the way that the incoming light is being converted to an electric signal, sent to a processor, and storage and later retrieval. Alright, so we're not going to go into too much details. There's a few slides with more details. If anybody interested in photography, this will be helpful. So I'll briefly show you the slides. Okay, so next application I want to talk about is actually the human eye. So let's look at some details of that. The human eye resembles a camera in its basic functioning, with an adjustable lens, the iris, and the retina. So here you can see, let me make it a little bigger. Parts of human eye. It works like actually like a simple camera, basic functions. So human eye, so the eyeball, and in the front there's this lens, and there's some additional layers also in front of it. Again, this is a convex lens, a biconvex lens. So let's say you're looking at something. Again, let's say you're looking at a tree. We're looking at trees today. The light comes in, creates an upside down image because it comes in the way it. So the lens has some focal point somewhere over here, somewhere in this region. It changes. This is not a fixed lens. These muscles on either side of the lens can contract, relax, and it can change the curvature of the lens, right? You can make it thin, you can make it thick. When you do that, and the lens is thin, these are not big changes, very slight changes. So you can move the focal point back and forth. That's how you can focus on nearby objects and distant objects. So it's going to create an image like this, an upside down image. So the top side of the tree will be over here, the bottom of the tree is over here, so something like this. And this back side, the retina, has these light sensitive cells called cone cells and rod cells. They capture the brightness and also the color. In addition to this lens over here, what is in front of it, this transparent region, is called the humor, aqueous humor. That also acts like a lens. So together they focus incoming light onto the retina. And then optic nerves will collect these electric signals and take it to the brain, and then the brain creates the image what you are seeing. Now you should read more about these things. The textbook should have much more information. You can Google, there's a lot of information. Have like a better idea, especially since you guys, many of you are biology students. Knowing these particular muscles and all that will be useful. So we're going to talk more about what do you call, let me make it small a little bit, corrective lenses. Like due to some defects in the eye, I don't know whether that's the right term, or some illness or something or the other, some accidents, not nerve damage, due to certain changes to the eyeball, the lens might not be able to focus incoming light correctly into the retina. To see a good image, the light needs to be focused right onto the retina. But sometimes, the lens, incoming light might focus at a shorter distance, like this. Or it might, the focal point will be too far. So it won't go beyond retina, but it appears like it's trying to focus over here, right? So what you get on the retina is a kind of a blur image. So these issues sometimes can be corrected using external lenses. Means you can wear glasses or you can wear contact lenses. So that's how you correct this issue. So depending on the problem, if it is focusing too short, that's one type of a lens you can use. If it is focusing with too much of a focal length, that's a different correction. A normal eye without any issues should be able to see faraway objects. We say that objects at infinity, and also nearby objects. So the eye should be able to change its thickness. The lens should be able to change the thickness in order to focus at different distances. When we say faraway objects, we pretty much talk about infinity compared to the image distance, which is inside the eye, which is probably few centimeters, 1 or 2 centimeters. Far away means like 100 meters away, 200 meters away, that is infinity. That's your far point. When we say nearby objects, the nearest, for a normal human eye, the nearest you can see without straining your eyes is about 25 centimeters. So normally we take 25 centimeters as our near point. Means if you are reading a book, looking at the cell phone, that is pretty much the comfortable distance for a normal eye, right? So sometimes for some people they have to bring it too close in order to see it, or keep it far away from your eyes, like much more than 25 centimeters in order to see it. That means your near point needs some corrections. So let's look at these issues in detail and see how to correct them. Nearsightedness. Far point is too close. So we're going to talk about two issues: nearsightedness and farsightedness. Nearsightedness means far point is too close. Another way to remember this is, when you say nearsightedness, mostly somebody with nearsightedness is able to see nearby things, but they're having difficulty seeing far away objects. So nearsightedness, you can see nearby things. Farsightedness, you can see far away objects, but you can't see nearby objects. Okay, so nearsightedness and farsightedness. Nearsightedness can be corrected with a diverging lens. So, alright, let's get into diagrams. Nearsightedness. I would say can see nearby objects. Can't see far. So in this case, what is happening here? The thickness of the lens inside the eye, it's too much, right? So when the thickness gets bigger, the focal length gets shorter. So nearsightedness can see nearby objects, so cannot see far away. So cannot see far away objects. So far away means light coming from infinity, parallel light. So here's the lens. Bends them too much, too short. Retina is over here, but it bends over here. It focuses over here. So what do we need to do? How do we decrease this bending? So incoming, so if you think about it, you have a lens, light coming in, it bends like this. So you want to reduce this bending. Imagine a light coming like this. If you apply the same amount of bending, right, let me change the color. Here parallel light. Now here comes some light not parallel. If we apply the same amount of bending, so this incoming light bends with certain angle. Now for this, it will bend like this, right? If we apply the same angle to it. So what we are trying to do is, when the light that comes from far away, we're gonna diverge them first so that it will correctly bend inside the eye, right? So we're gonna diverge them first. The parallel light that comes from faraway object. So we say that if something is at infinity, the light coming from that object is mostly parallel lines. So here comes parallel lines. We put a diverging lens first. So we put a diverging lens over here. So that's what the eye doctor would do. Check different lenses to see which one gives you the right amount of bending. So here comes parallel light. It's diverging, so it bends outwards, and then correctly focuses into the retina. So nearsightedness, or if you can't see far, this issue can be corrected with diverging lenses. Now, there are things to remember. Actual issues will be a little bit more complicated than this. Some people might have both nearsighted, farsighted issues. So, and also you might prefer wearing contact lenses rather than glasses. Or some person might have a preference, they want to wear glasses. So the eye is over here. This is eye. If you wear contact, it's going to be a layer right on top of the eye. If you wear glasses, there is some gap between them. So you have to consider all these distances when you do these maths. So it's a very complicated but interesting field. So I'm not going into all the details. We just stay with simple stuff. Right. Once again, nearsightedness can be corrected with a diverging lens. Now you see what's happening. We're going to diverge them first so that we can control too much bending. Farsightedness with converging lens. Okay. Let me take a new page. Now farsightedness. Oops. This should be one word, okay. Farsightedness means you can see far, right? You can see far, but not nearby objects. So what happens when you're looking at, if you're looking at a faraway object, parallel light will focus without an issue. But nearby objects, light is not parallel, right? If you're looking at something close by you, say you're looking at a pencil on the table or some little object like that. Here's the lens, the rest of the eye. Light is already diverging kind of light. They focus over here. They're supposed to focus over here, but the actual focal point is too far. So what do? We will put a lens in the front. We put a convex lens and try to converge them a little bit, because the eye is not able to converge them. Like ideally they should be converging like this, right? Ideally it should be converging like this. So it needs a lot more converging power, right? It's not converging enough. So what we will do is we'll place a converging lens in the front and get them converge a little bit. We'll help the eye and get them converge a little bit, and then I can the human eye can converge the rest of it. Okay, so the farsightedness, if you can't see nearby objects, you can use a converging lens. Okay, so let's try an example. Okay, how do we do this? Alright, don't look at the diagram yet. Now let's see what the issue here. So let me clear this one more time. Sue is far-sighted with a near point of 100 centimeters. So the person can, so here's the, okay, hold on. Right, so here's the person's eye, and ideally the near point should be 25 centimeters, right? Ideally. But this person, in order to, let's say she's trying to read a book, she has to keep the book 100 centimeters away over here. Object has to be here in order to get it properly focused. So which is quite uncomfortable if you're trying to read a book and keep it 100 centimeters away. So we need to bring the near point to 25. That's the ideal distance. So what do? We're going to use a lens. Now, when we apply the lens equation, even if you don't know what kind of lens you need, the answer gives you the right type of the lens, right? So let's see how to formulate this. So let's say you put some lens in front of the eye. Now it says it's pretty close, so it's like almost like on the eye, and you place the, so let me redraw this diagram, right? Here's the eye, so you put this lens right there, and then you put the object 25 centimeters in front of it, because that's what we need to do. We need to read a book keeping it 25 centimeters in front of it. That should be our right near point. So we keep the object there. So the object distance DO is 25 centimeters. This lens, this new lens, the second lens, external lens, should create an image at 100 centimeters, again in front of it, in front of the eye. So the image should be at 100 centimeters. The eye should be 100 centimeters. So then the human eye, this person, Sue's human eye, can see that image at 100 centimeter and recognize it, right? The object is actually at 25 centimeters from her, so she can place the book at a comfortable distance. But this artificial lens will create an image 100 centimeters away where her human eye can see it. That's how we're going to correct this. So now look at the way we are setting up the equation. DO has to be 25. DI has to be 100 but negative. It's a lens, so if it is in the same side as the object, the image distance is going to be negative. So we create that, and then the human eye portion can read it. So let's try the equation. 1 over DO plus 1 over DI equals 1 over F 1 over 25. This is negative 100, so negative 1 over 100 is 1 over F. Common denominator 100, 25 times 4, so 4 minus 1, 1 over F, 3 over 100, 1 over F. This gives you F equals 100 over 3, which is 33.33 centimeters. You see, we have a focal length of 33.33 and we have a positive number. That means we are looking at a convex lens of F equals 33.33 centimeters, or you can say 0.33 meters. So we decided what kind of lens we need and how much the focal length should be. Now, it says assume the lens is very close to the eye. So in certain problems you'll see that, like especially if you're wearing glasses instead of contact lens. Now this works fine for contact lenses, right? Because there's no distance between the artificial external lens and the human lens. But if you're wearing glasses, this is the human eye, this is the lens, the artificial one. That is about, depending on what kind of glasses you're wearing, probably like 2 centimeter gap. So when you measure these things, you have to consider those factors, right? 25 means this will be 23 object distance changes. Okay. All right. Now this question has another thing I need to discuss. So she wants to use reading glasses. So what lens power? It's asking the power of the lens. I don't remember whether I discussed this in a previous video. Probably I did. But we calculate the focal length, focus. But when it comes to things like reading glasses, or when you go to eye doctor, they use this term power, right? Power is actually when the focal length measured in meters, power equals 1 over f. That's it. But the length has to be measured in meters. So in this case, what's the power? 1 over 0.33. What is 1 over 0.33? Something like 3, I guess. 1 divided by 0.33 is 3.03. 3.03. Maybe I have already discussed this, right? Power comes with the unit of diopters and it gives us D. Now, because this is a positive number, you say it's positive 3.33. That's your power, positive 3. So if you just going to buy a reading glass, you go and pick one that says plus 3, right? It's in diopters. Diopters, in other words, it's 1 over meters. That's the meaning of this unit. Okay. So if it is just focal length, you calculate it. If it is power, you get the focal length in meters and take 1 over. Okay. Moving on. Alright, so next question, actually I'm going to give you an example. Let's say there's a nearsighted person, right? So the person is nearsighted and the far point is 2 meters. That means pretty much this is the maximum distance the person can see comfortably. Person can read nearby objects, like he can read a book at 25 centimeters, but he can't see things beyond 2 meters. Things gonna get very blurred. So how do we correct this? Far point is 2 meters. So let's say here's the person and the eyeball and the eye looking at a tree far away, right? He won't be able to see this clearly. But if the tree is over here, 2 meters from him, he can see it clearly as a faraway object. So we need to bring this tree, we need to create an image of the tree 2 meters in front of him. This is the object. DO is over here. So we're going to put some kind of lens in front of his eye. That lens will, for an object that is far away, DO, which is at infinity, will create an image DI at 2 meters in front of him, so that he can, his human eye can read it as a faraway object. Now remember, okay, let's try to, so DO is going to be infinity, DI is going to be 2 meters, but again in front of the eye, so that has to be negative 2 meters. So 1 over DO plus 1 over DI, 1 over F, 1 over F, 1 over infinity minus 1 over 2 is 1 over F. 1 over infinity is 0. 1 over F, we have 1 over F is 1 over 2 negative, f is negative 2 meters. We need a focal length of 2 meters. What kind of lens is this? This is negative, means it's gonna be concave lens with a focal length of 2 meters. So a diverging lens. Now what about the power of this? Power is 1 over f, so negative 1 over 2, negative 0.5 diopters. Okay. So this is how you correct a nearsighted eye and give the ability to see faraway things. Alright, let's see. Here's another one. Little bit of a challenging question. I will let you try that. Okay. I'll give you the answer to the first part. It's gonna be 15 centimeters. Okay. Think about the second part. Let's move on. Some interesting conceptual information. Magnifying glass. When we use a magnifying glass, just one lens to magnify something, we use convex lens, and we keep the object really close to the magnifying lens, really close to this convex lens. So the idea is the object will be inside the focal distance. So you are looking from the other side and it creates this magnified virtual upright image. Alright, let's look at few more conceptual information. So telescopes, refracting telescopes, the basic one has two lenses, the opposite ends of a long tube, two convex lenses. The objective lens is close to the object, so, and the eyepiece, the other convex lens is one that closer to your, where you place it next to your eye, is called the eyepiece. So basically the ray diagram looks like this. Objective, you're looking at something far away. Light could be parallel to the principal axis, or it could be just parallel but not really to the principal axis. Either way, it creates an image. If this is far away, it creates an image right by the focus of the first lens. So the objective lens, this FO, is the focal point of the objective lens, that FO. And then you place the second lens in such a way that this first image is inside the focal length of the second one, this FE, eyepiece focal length. So then you're looking at it from this side. It creates, because it is within the focal length, it creates this magnified virtual image, right? So this is how the simple telescope works. There are reflective types of telescopes also, using concave mirrors. So incoming light reflects into a small mirror placed in front of it, then taken to the side, and then there's a lens to magnify it. Now the telescopes we used to see, used to watch the sky, like moon and the star kind of stuff. We don't really care about whether the image is upside down or not, right? Whether it's upright or not. But for terrestrial telescopes, like bird viewing and spyglasses kind of things, it's more convenient if the image is upright. So here the 3-lens system, you create this upside down object and then put it upright using a second lens. The third, they call it the third lens because the middle one, and then the eyepiece will magnify it. Same thing you can do with this one, concave lens. This is just for you to have a conceptual idea, right? We won't be doing any math problems using this. Microscopes, something you use often in your biology studies. So here you have a small object. So the object is going to be much closer in this case, not like a telescope. So it creates a little larger image, right? The first magnification, a real image, and then the second one is going to make it much bigger. So this is a basic microscope, but an advanced one will have more magnification steps, and we can show using simple math, means using the magnification equations. If you have a 2-lens system, the magnification becomes the product of the magnification from each lens. If the first lens makes a magnification of, for an example, let's say magnification M1 and second lens M2, the final magnification will be M1 and M2. So if first one magnifies it by magnification is, let's say, 3, and the second one's magnification is 4, the final magnification from starting point to the end point will be 3 times 4, 12. And then you can see what kind of advanced optics the microscopes you are using would have, like the magnification is like 100 times or 200 times. Let's see what else we have. We don't need the microscope equation. Some defects in lenses and mirrors. One common issue is aberration, spherical aberration. They do not focus onto the same focal point on to fix like a. Oops, sorry about that. Let's minimize this. To a fixed focal point, they bend differently. Solution: compound lens systems. Use only central part of the lens. Only the middle part, don't go to the edges. Can avoid that. Chromatic aberration. When it comes to colors, different wavelengths bend a little differently. And this is how we actually separate the light into all the rainbow colors. But it's a problem when it comes to optical systems like telescopes or microscopes. So they do this kind of achromatic doublet of lenses of 2 different materials, so they each compensate the bending, each other's bending, right? Okay, finally, here's a summary of things we discussed. The lens equation, same goes for the mirrors. Magnification, and that's it. Alright, keeping it under 40 minutes.